right, yeah. So today I want to talk mostly about deep neural networks, but since I didn't quite finish to talk about unsupervised learning last time, we will first go a few slides back. Oh, it doesn't, I should switch this on, so let's see. Okay. And I basically want to wrap up the unsupervised learning part from the last lecture. And the motivation was, to remind you, it could we learn the feature spaces that are generally useful for vision. And the approach following Barlow's suggestion was unsupervised learning. And the main idea was that if we think of encoding images in terms of a generative model, then such generative models would allow to encode the information in an image with much less bits, so in a much more efficient way. And so redundancy reduction, reducing the amount of bits that you need to encode the image without losing any information, so lossless compression could be a strategy to find representations that are similar to a computer graphics model. Of course, only if you choose the right architecture. And the approach that I've been taking, and I've showed you a couple of models, is something I call Minimax Modeling, or I think Neuroscience sometimes calls it onion peeling, because what you do is you use maximum entropy models, which fulfill certain constraints. And the simplest constraint that you can fulfill is that you reproduce the histogram of the individual pixels. And if you do that, and otherwise you assume independence, so that would be maximum entropy, this would be a typical sample from that ensemble, and that, of course, looks very different from nature images. If you now, in addition, say, match the autocorrelation function of nature images, and otherwise you don't make any assumptions, you want to find the ensemble with maximum entropy, you will get images that look like this, so they have much more smoothly varying images. So in that sense, they are much more similar to photographic images, but of course you still don't see any objects here, and they're also still far away. And then by specifying more high-order correlations, you will get more interesting stuff in the image, and that's the part basically that explains this mini. So if you have maximum entropy models and you try to reduce the entropy of maximum entropy models, then these ensembles become smaller and smaller, and you kind of try to approach the set of nature images here. And this approach is important to distinguish from synthesis models, which do not bother to make sure that they include all nature images. So you can have a lookup table, of course, that would be something like Flickr or Facebook. You can download lots of images. Say a set of billion images, you would have probably a hard time to remember each individual example, so it would look very variable to you. But it is nothing compared to the number of nature images that exist in the universe. So it's even if you have 1 billion images, that's nothing compared to the exponential complexity. And I kind of ended in the last lecture with the pixel recurrent neural network, which I think is I'm pretty sure is the new state of the art in this Minimax modeling approach in terms of minimizing the cross entropy and thus being the minimal maximum entropy model containing the set of nature images. And the samples of that model look already very natural, very intuitive. And also the numbers are so very impressive, so that they have a table where this is the cross entropy basically. And this was the previous state of the art. And they achieved even a jump of 0.47 bits per pixel, which is a lot. So if it's about higher order correlations, it becomes harder and harder to explain away more pixels. Regarding the evaluation of generative models, it is quite instructive to make sure to understand the difference between an evaluation in terms of likelihood or cross entropy and evaluation based on image samples that we get from the model. So, of course, if the model generates nice pictures, then that is nice, yeah, and intuitively accessible. And but it is hard to say how much variability there is actually in the images that are generated if you don't quantify the entropy of the model, right? And so one way that people have tried to get around this problem, that to estimate the entropy, is just to compare the nearest neighbors in the training set in order to verify at least that you don't learn a lookup table, that you see that your model does nothing but memorizing the individual samples in the training set. However, the Euclidean metric is not a very good metric to make sure that this introduces actually that your model has really learned interesting generalizations from the training set. So what you can do, and this is basically the suggestion here to how to cheat on image modeling. You could build a Gaussian mixture model where you have a Gaussian centered on each training image. But the training image is sort of transformed with some simple transformation in order to make sure that the nearest neighbor matches in the Euclidean distance are not the ones in the training set, right? Or whatever the evaluation criterion is. And in this way, you can make sure that you get nice, basically perfect image samples which are different from the training set. And in order to make this point, illustrate this point, I also made an example here of 3 images. And of course, perceptually, you would think that these two are very similar. But if you look at if you plot the pixels of this image against the pixels of this image, the correlation is 0. And if you plot the correlation of this image against the pixels of this image against the pixels of that image, the correlation is about 0.9. The way how I achieve that is by adding just a gradient, a lightness gradient from the left to the right. So here in these 2 images are both bright at the right side, and this is bright on the left side. And I adjusted the gradient just to make these 2 being orthogonal, these 2 images, and these being as correlated as possible. So this is a way how you can make these 2 images being completely different so this would never be observed as the nearest neighbor of that one, basically, in such a model. The other interesting observation is that the quality of synthetic images has no necessary implications for the likelihood. And that can be seen by, this is again written as basically in the way, if you want to cheat, on getting high likelihood image models maybe, and nice samples, then you would take your distribution which generates high likelihood, and you would take another distribution which is basically a lookup table, which just samples from the training set or some transformed versions of the training set. And most of the time you sample from this lookup table model, and only very rarely you sample from the model with a high likelihood, that generally has a high likelihood on edge images. So since this expression here can be lower bounded if you just use this part, so these are both positive terms, so we get a lower bound to this by skipping that term, and we can decompose this actually I'm missing a log here, since, okay, this should be log of p published is larger or equal than the sum of these logs, because this product can be turned into a sum. And since images are very high dimensional, so this term here is of order n, and this term is only of order 1. And so even if you only sample with a very small probability from the model with high likelihood, it will dominate the likelihood of this mixed model. So in other words, if you have a mixture model where one component generates nice images, from which you sample most of the time, and another model captures the true distribution of nature images as good as possible, this is a way how you could get basically perfect samples for all practical purposes without being dependent on the likelihood. And one way, I think, to verify that would be that one compares the model entropy to the data entropy. So by adding this term, of course, you would reduce the model entropy a lot. And that could be a test. Okay, in the pixel recurrent neural network paper, they did another test, which I think is a good test, which is image completion, because there, in order to be able to do image completion, you don't know what kind of image you have to complete in the future. So you can test on new arbitrary test images, and you can see how well the model can fill in missing parts. And you can also test how variable this filling in procedure is if you sample from the posterior, right? So in that sense, you get a good notion of how well the model, how convincing the completions are, and also how variable the completions are. And I think this is, so since likelihood computations are quite demanding, this is a nice practical test if you don't want to do them. Okay, so I added some literature here to the slide. So I uploaded the slides, by the way, so you can have them as reference later. And now I want to wrap up basically the lecture from yesterday before I start with the lecture from today. And so yesterday I first gave you a very simple example for the curse of dimensionality, and with the warning of not putting too much belief into learning, or into just letting the data tell, but it's always, you should use as much knowledge as you have and think about how to combine the knowledge in the best way with the data. As an example of a nice standard regression framework, I introduced this NLN cascade regression, which is basically the generalized linear models with some additional feature space embedding in front. And as an example of going beyond that standard framework, so this is something you can always do, which will always give a good baseline prediction. I introduced a model based on a mixture model, which can be seen as a nature extension of these generalized linear models, where instead of having just a linear filter here, you have a couple of quadratic terms, and you have several logs of them. And so the more logs you have, the more non-parametric your model becomes. So in principle, if you have arbitrary data, this has universal approximation capabilities, and seems to provide a nice trade-off between the possibility to optimize it, to interpret it, because you have a full probabilistic model for it in contrast to a neural network, and flexibility. And finally, I was talking about nature image statistics, so this should only show up now, but somehow I used to combine it, and I talked about the Minimax modeling approach. Okay, now let's turn to deep learning and the question, can we learn feature spaces with a different approach than unsupervised learning? So unsupervised learning is like the nature application of unsupervised learning is feature-based learning because you want to be task independent and you want to use lots of data and so that was also why I was using or trying to build representations via unsupervised learning for a long time. And surprisingly, so that will be the take-home message of the next 15 minutes or so, the best strategy at the moment to learn good features, at least in vision, is a supervised learning strategy on a very specific task. And but the surprising thing is that this task is sufficient, has basically imprints sufficient knowledge into the network such that the network can be used for all kinds of other tasks. And here are a couple of papers which make this point of so-called transfer learning. This is to train on one task and you use that knowledge. The knowledge is then transferred to another task that you actually want to solve. And so if you have one task where you have lots of labeled data available, you can use that task in order to pre-train your model, and then you go to the domain of that you're actually interested in. And to me, this paper here actually was the paper that turned me into a deep neural network guy. So it was uploaded on Archive in autumn 2013. And before, I was always very skeptical. So I will mention that later again because, yeah, I will come to that again. So first, let's introduce the Imagenet Benchmark, which is probably the most important benchmark in computer vision these days. And it is very simple, very similar to MLSS, handwritten digit recognition, just that instead of handwritten digits, you have photographic images here downloaded from the internet. And instead of 10 categories, you have 1,000 categories. And for each category, you have 1 million training images instead of 5,000, I think, in minutes. So it's scaled up. Basically, the hardware has scaled up, the internet has scaled up, and so it's a scaled up MLSS learning task. And yeah, I mean, there's something is also intriguing about this Imagenet benchmark, that not only you have to distinguish course categories, but there are also all these distinctions between different types of cats and different types of dogs. And yeah, that I'm not sure whether I would be able to do that. Definitely not in English because I don't know different type of dogs and the names in English. But yeah, maybe that's important to some extent, I don't know. So in 2012, it was for the first time that the neural network won this benchmark. Yeah, and that already was great, or perceived as a great success of neural networks. Yeah, because before no one were really using them. But as I said, I wasn't convinced because yeah, a large task. This network has lots of parameters, and so my general suspicion was against these type of learning tasks that you heavily overfit on the particular task. Yeah, so I would believe, or I believed, of course, that it generalizes within that data set, but it wouldn't generalize to other data sets. And there's this suspicion has also been quantitatively investigated in 2011 by Tony Tuiva and Yosha Efros, where they compared where they determined the drop of performance of vision algorithms that have been trained on one data set and then applied to one of the other data sets that are available. You don't have to go through this entire table. Basically, the average drop is 30%. So it is quite a substantial drop when you try to generalize from one data to the other. Okay, so what now seems to work to an extent that didn't work before is that when you train your network on, or another algorithm possibly too, but the neural network, I mean, you only have this proof at the moment for neural networks. If you train that first on Imagenet, for which you have lots of data available, you can afterwards chop off the upper layers, the top layers of the network, and use the rest of the network as a feature vector that similar to a SIFT feature or a hot feature vector, just that it is much more powerful. It has much more knowledge required. Okay, so if you do this with AlexNet, the benchmark Imagenet winning network of 2012, and you use this transfer learning strategy on Pascal Bock, you leave the previous models quite significantly, especially given that usually the performance doesn't go up like this, but rather saturates towards the end. And the main achievement here is that you basically use the knowledge acquired from the other data set. Yeah.
When you said you use the network as feature without the last layer, you use all the net as feature or only the last before last layer?
So I probably was on purpose a bit sloppy. So I will show you an example where we only chop off the top layers and really left all the other layers fixed, and then learn a simple linear classifier on top. Other people, or you can of course also do fine-tuning of the lower layers, and you can try to readjust the lower layers as well on the new data. But it also works if you just, so in the simplest scenario, you just keep the lower layers of the network as is, as a fixed transformation, and then you train a new classifier on top. Was that your question?
Yeah.
So,
I think that you mentioned that you are using the representation, just the numbers that come out of the last layer, or if you are also keeping the intermediate representation that's fitting into the classifier.
When you're using your network, not as a classifier, but as a way to extract feature of the images. If you use only the last, before last layer as feature, so you can use all the previous layers as features.
Usually they use only the last layer, the output layer.
Because the first layers have high dimensionality. They are very, the dimensionality is skewed, so it's very hard to do some classifier if you have to.
But yeah, so I will show you an example where we actually can also use all the layers. Okay, so the idea basically is that after you train these lower and intermediate layers, that hopefully they are useful for all kinds of tasks, like object detection, depth estimation, image segmentation, and so on. And so I haven't really said much about this network yet. So one thing, of course, that is important is that these are convolutional neural networks, which saves you a whole lot of parameters, because all the neurons are required to have the same receptor fields at each location. And this is also similar to biology. Oops, yeah, okay, so that point I will make later. And yeah, maybe so much for now. So basically each a layer consists of many feature maps that are obtained by clear convolution and some nonlinearities in between. And so the images become more and more abstract, converted versions of the input, but they are still in the spatial arrangement like the image. And at the time when I got interested in using this approach, we were working on saliency prediction, so on predicting where people look in images. And I will make first a little detour on what we did on saliency prediction, because what we did was we worked on the model comparison of these models. So we didn't intend to build new saliency models, but we only tried to remove some inconsistencies that there were in the benchmarking of these models. And so I think that's also quite interesting topic. So if you have a benchmark, it's always important that you can somehow agree on what your quality measure is. And I will first tell you about this quality measure, and then I will go back and tell you how the strategy of using the Imagenet feature vector for solving the problem of saliency, for solving the problem of predicting where people look in still images, worked out. Okay, so here's the problem. You have images and for which are presented on a monitor screen to human subjects, and where they were instructed just to look at the images in a free viewing condition, so there was no task besides not falling asleep. And so they had the time. So the first 10 or so fixations were recorded. And so there's a data set from MIT with a bit more than 1,000 images. And you now have for these images basically these points where people looked. And so you can determine, based on these points, you can determine the average density, average over all images where people tend to look. And then you see, on average, they tend to look into the middle of the image. That's not very surprising. So there's some center bias. But you can also try to non-parametrically estimate where people look for conditions on the image, for one particular image. And like for this image here, this would be one, I think it's a kernel estimate of the density of these fixations. And the amount of information that is available from the content of the image about where people look can be evaluated by the difference between these two distributions, right? So if you know about information theory, what you want to use, or how you would quantify the amount of bits that this information of the image content gives you about where people look, you just have to evaluate the Kullback-Leibler divergence between this posterior distribution and the prior distribution. And yeah, so we will use this average over all images as the baseline model, which doesn't depend on the image content. And we use this non-parametric estimate as a gold standard. Of course, we could probably do better than the gold standard if you had more fixations, but it's a good way to see how good we are, or how good the models are in predicting these distributions. Okay, as I mentioned, so the purpose of saliency models, of bottom-up saliency models, is to basically predict the posterior distribution based on the image content. And this would be the measure that I would consider a natural measure of quantifying how well a model does this. But interestingly, this measure wasn't in the list of the measures on the MIT Saliency Benchmark site. There were a couple of related measures, but not this one. To give you also an intuitive account of what it means to measure the information gain. So imagine your prior distribution is a uniform distribution within this ellipsoid, and now you have one bit of information explained by the model. That would correspond to a shrinkage of this uncertainty where people look by a size of 2 to the 1 divided by 2 bits. So it would be this size. And if you had no 2 bits, it would shrink to this size, 3 bits this size, 5 bits this size. So it's something very intuitively accessible if you think of it in this way. So basically the scatter is, well, the measure measures how much the scatter is reduced, not only for this uniform distribution, but for arbitrary distributions. Okay, so the benchmark site uses 8 different metrics. And interestingly, depending on which metric you choose, you have a good chance that your model pops up at the top. So they are not, the ranking is not consistent across these different metrics. And this is how the different metrics look for different models, for which, as a function of the information gain explained. So this was our measure, and if all measures were consistent, they should all somehow be correlated. They should all be proportional. Yes?
I guess the measure also has to take into account whether you are actually decreasing the probability in the right places. I mean, there is some traces of where people actually miss. You could make the probability distribution arbitrarily small by multiplying it over 0.
Right. That actually, yeah, we will, it does. So what we do here, okay, I was too quick about this measure. This expectation here is taken over the actual distribution where people looked conditioned on the image, and then averaged over all images. So this is again something like a cross entropy and not the entropy itself. So if the model would have like would bet that you look here and you try to trick me into look here, then you would have infinite log loss, and so this would be very bad. So that's why models can even have negative performance. And that's actually what comes out here, that several models, so each column here corresponds to one model, evaluated by different metrics. And you can see that several models actually have negative information gain displayed. All right. And so this is the correlation matrix between these different measurements, so they run very correlated. The main problem is that in the definition of the saliency metrics, people haven't specified the units with which saliency is measured. So basically, for convenience, and one can argue for good reasons, they only looked at the contour lines of the densities. So that means the saliency measures in the past have been invariant under pointwise nonlinear monotonic transformations of the saliency measure. Okay? So that would preserve the contour lines, the two-dimensional contour lines, but you don't know in which units you actually measure the saliency. And that means you cannot take integrals over saliency maps. So if you want to evaluate based on the previous definitions of the saliency map, how much more probable it is to look at the left side than to the right side, then for, if you think in terms of probability distributions, the nature way would be to integrate over the left side and to integrate over the right side and then compare the two probabilities. But if you only specify your probability distribution up to a pointwise nonlinear transform, then you cannot do that anymore. It has no, I mean, if the models are not trained in the way to also predict this pointwise nonlinearity correctly, then the integral will be off. And that's basically what we accounted for. So we retrained the existing models by adjusting the scale. And after we do that, actually all these different measures become proportional to our information gain, which is very nice. Okay, that was, and so here's the correlation matrix. So it's 0.9. Nevertheless, I personally like my measure best because I can imagine the bits very well, what they mean. And it also, because it puts things on a ratio scale, so you can actually evaluate the differences between the models. It makes sense to compare the difference between two models. Yeah. And it also makes sense to compare the difference to the gold standard. And at that stage, so it was about 1.5 years ago, or 2 years ago, I don't know, something, maybe 2 years ago, the models were, the best model was at 34%, explained 34% of the explainable information. And that was a three-layer neural network already. So it was called an ensemble of deep neural networks. So, yeah. But this neural network was only trained on the MIT dataset. And our idea now was to do this transfer learning trick. So we, at that time, we took the AlexNet neural network and we did something super simple. So we just extracted all these convolutional feature maps and upsampled some of them, and so that to bring all of them on the same pixel size. Yeah, so usually there's some pooling in between so that not all feature maps have the same number of pixels. So you bring all of them to the original pixel size. And then you only try to learn weighting coefficients as a linear superposition of these feature maps. We try to predict the saliency maps, the densities that we can look. Including the center bias as an additional prior knowledge and using a softmax nonlinearity. And if you do that, you get a performance of 56%. And at that time, when we did that, we already knew that there are new neural networks coming out from the Imagenet Benchmark. And that's why we called it Deep Case 1, because we thought, okay, if there are better models coming from the benchmark, then maybe that knowledge also transfers to our problem here. And so maybe when we have Deep Case 2, Deep Case 3, and maybe at some point Deep Case 9, then we will have solved the problem. With very little effort on our side. So basically we let the other people do the work on training on Imagenet, we take the features and then solve the saliency problem. So the other model that achieved actually super good generalization performance is the BGG19 network from the Neuroscience group. You can see that its transfer learning boost on Pascal 2 is really amazing. It's larger than the entire improvement of the years before neural networks were used. And so this is how we visualize that network. So I will explain it in more detail later. For now, it's just a sketch. And we used the same strategy. So we extracted the different feature maps. We did, so of course, then you try to, at some point, you try to do something a little bit more intelligent. So we added 2 convolutional layers, which are only 1 by 1 pixels. So they only basically convolve across feature maps, and you add some nonlinearity in between. So it's not linear prediction anymore, but it's still very, very simple. And by optimizing that network, we were managed to get up to 88%, explaining 88% of the expanded information. So I will show you a few example images for those. And so here, the x-axis shows you the different image indices, sorted for the gold standard. So in terms of, so the blue line here shows you the gold, how much information gain the gold standard, basically the posterior distribution has relative to the center bias based on the gold standard. And so the best images in this data set had more than 4 bits, and the worst images had less than 1 bit. So for some images, also like empirically, you cannot predict more than whether people will look left or right on average. And these black dots show the information gain of the ensemble of deep neural networks model, which didn't use this transfer learning. And so now these are the information gains of deep case 1, and this is how it looks for deep case 2. So as I mentioned earlier, so you can have, it's possible that you can have higher information gains because also our gold standard, you can have higher information gain than the gold standard because also our gold standard is an estimate. But that estimate uses actually empirical data of where people looked rather than predicting where people look just from the image content. Okay, and here for illustration is what these bits mean in terms of how much the scatter shrink. And now we will look into those images here. So for which the gold standard has the highest information gain. And as you can see, these are very special images where, of course, things are rather predictable. This is the gold standard, the density of the gold standard. These contour plots divide the image into quantile, so it's always 25%, 50%, 75%, but you cannot really see the differences in colors. This is deep case 2, deep case 1, and TDM. But you can see even for these simple images, there's already a difference between deep case 2 and deep case 1. And then here these are the 3 images on which deep case 2 performed the worst comparing to the gold standard. And these images are pretty crazy, so also the amount of information that you can predict is relatively low, it's about 1 bit. And it's not clear that, the model at least has still a positive information gain here. So for no image, deep case 2 has a negative information gain. If you plot the information gain difference between deep case 2 and EDN, you can see that for almost all images you get an improvement. So it's not just by randomness or that there are systematic errors. And the biggest improvements are for those images which contain text or faces, which indicates that you're using the knowledge obtained on Imagenet for detecting things like text or faces to predict actually where people look, because these are salient things. So in this case, it's very obvious that it should transfer, right? Because we kind of know that faces are something salient to humans, and also text is something salient. And so that was one of the intuitions why transfer learning from Imagenet to saliency should work quite well, as it did. Okay, we did further analysis, but maybe let's skip over those. There are lots of work since then where people use feature vectors of BGG, or now BGG is a very popular network which works on many things, but also other networks, and applied it to other problems like image segmentation, depth inference, object detection, and so on. And interestingly, since I'm a neuroscientist, I mentioned this too, it also works very well in predicting neural responses in the visual pathways. So the best features that we have at the moment to predict neural responses in the visual pathway, in particular in upper regions, are those obtained from neural networks that perform the best on Imagenet. So there's a correlation in performance and performance-optimized networks on how well they perform on Imagenet, in how well they perform in predicting neural responses. I mean, it's not, so we need much more analysis to make this a rock-solid result, and there are many questions that you can still ask about this, but I think it's not meaningless, so it's a promising indication.
So in the visual cortex, there's a lot of, I guess, information feeding down from the upper brain, whereas the network isn't feeding up. So is there perhaps a, the sort of recurrent brain are a bit different to the kind of architecture that you have before the network? Is that something you have any comments on?
Yes, sure. I mean, that's has been a long-standing question in neuroscience all the time. What is the role of the feedback? So anatomically, we have lots of feedback. Interestingly, in terms of electrophysiology, so in record spikes, the effect of feedback is much more subtle than if you use fMRI, or also local field potential shows more of feedback than the actual spike activity. And one model is that there's like a feed-forward, where the inference mostly is done in a feed-forward fashion, and then you can speculate about the role of feedback. So no one knows. Possible candidates are that they do something with leaf propagation, some backward path in the inference, right? So in order to bring information about large-scale inferences down to small-scale variables, or it could also be on this. My favorite hypothesis is that it's more used on a slower time scale to switch between tasks. But these are exciting questions where I would say it's also, to make these questions more precise, it's very useful to have these neural networks which can do inference quite successfully in a straightforward fashion, because it makes also generates clearer hypotheses whether you need feedback for inference or whether you use it for other things. Learning is another candidate, right? Somehow you want to back propagate the information. But I don't want to overemphasize. I mean, there are lots of differences between them. But what's interesting, and I think one important point is, so object recognition is a really hard task. And computer vision has worked on this for decades and is still not solved, right? And in order to solve this task, you can expect that there must be similar computations being done in different systems, but even though the actual implementations can be different. And so I expect that similar representations emerge in any kind of vision system that tries to efficiently do visual inference. We're not excluding that there might be like a few completely different ways, but it's the complexity of the task is a strong constraint on the systems. Was there a question?
Yeah, that was a perpendicular question in a way. So, if I understand what the model explains the saliency based on the content, but a photographer would say that there's also other thing that affects, or there's a light where the light is concentrated, intensity of the light in the picture, and also which one is in focus, which part is in focus or not. So if the parts that are more in focus attract more the eye. So is that?
Well, would still be, these type of things could still be learned. I mean, we haven't analyzed and told them apart. When I meant content, I didn't mean content opposed to appearance aspects, like lighting conditions or so. I meant opposed to center bias, basically, to things that have nothing to do with the image. So any information that you can extract from the pixel intensities could in principle be used in the saliency models. But what cannot be used, for instance, is, I haven't shown you results where things like the dynamics between consecutive fixations, put constraints on where people look, and in tasks, of course, if you give subjects a task, then the patterns will become completely different. But if you have movies, so this is really the simplest setting that I told you. Okay. Yeah, so this fact that you have a strategy, you have a data set which allows you to get useful features and then transfer to many different other tasks, so that's a quite empirically quite well confirmed finding, is part of the, I would say, probably one of the main reasons why we have this explosion in neural networks, right? Because if I have to solve a vision problem, of course I download a neural network first that has been trained on Imagenet, so I don't have to do all this work again, and can use that knowledge to solve my new problem. And that is a little bit similar to biology. Something useful has been found, then this can, and which transfers to other things, this can generate a variety of things. And so it's kind of nice for computation neuroscientists because now we have in technology a similar situation than we have in biology. So we get neural networks that do something interesting, and we don't have the right language or the right theories yet to understand what's going on. And so for me as a computation neuroscientist, this is also like an acid test. Are we able at least to understand these technological neural networks for which we have the full wiring diagram, for which we can record from all neurons simultaneously? And would we then say, just because we have this full wiring diagram and we can look at all the variables, that we have understood what this network does? And so it's really an opportunity to develop theories, or to develop a language, or frameworks, how to distinguish between different neural networks and how to establish meaningful similarities. And that motivates now the second part of my talk about how can we probe all the information that is represented in these neural networks. And so now I'm going to first show you a little more about the VGG19 network that we are using here in the following all the time. And if you feed in an image like this, these are the feature maps really computed for this image in the Conform 2 layer, so it has certain numbering here. So the first number always refers to whether you're before the first pooling step, after the first pooling step, and so on. So how many pooling steps you have in between, and the second number is then which layer you are in between these pooling steps. And the first layer you have 64 feature maps, then 128, 256, 512, and the highest, the Con5 layers, 512 feature maps. So in the beginning, that's maybe also good to know, yeah? So you're 64 times overcomplete. So you wouldn't expect that any information is lost. Due to the pooling, during the pooling, information gets lost. And at the top, we would expect that some information is lost in the network, because there, if you count the total number of variables, it's half the number of pixels in the setting that we are looking at. And yeah, so one question to ask is, given the activation in the network, how uniquely is the input determined, right? So how invertible, how lossless is the network? And also another question to ask is, if we feed in a similar image, what kind of where do these differences show up? And how does the image generalize across appearance changes? And the strategy that we were exploring to address this problem is pre-image search strategy, where, so other people have done this before, so I just want to explain the way how it works. So here we are looking at the feature maps of conv.2, and we are now asking for a set of images that leads to very similar activations up to some very small loss in the square distance of the activation. And one thing that you can do to do this is you start from a white noise image, and then you do gradient descent on the image pixels to minimize the square distance between the activation of this image, of the current image, and the target image that you used in the beginning. So if this is your target image, which specifies here your y0, you then search over ux in order to identify, to find a new set of, new image in the set of all possible images that have very small distance in the activation of this one. Is it clear? Okay, sorry for messing up a little bit the explanation. So if you do that for the first layer, as I said already, you get the original image back. Also later, there are only very small perturbations. And for the conv5 layer, you get some visible loss of information. So the high spatial frequency information is lost. But the content is still well preserved. Yeah.
You start from random noise here?
Yes, yes. So
this somewhat contrasts the result where they find the adversarial image, where they start from the image and then can perturb it very slightly so that you can't recognize the difference, but get completely different outputs of that side. Do you have any comment on how can both of these coexist?
Yeah, so the adversarial images, first, so we are looking here only at the convolutional layers. Okay, so I forgot to mention this slide subtlety, which is not so subtle. So these, after the convolutional layers, there are 16 convolutional layers, and then there are 3 dense layers. And so the way to think about it is that the convolutional layers are the feature vector, or the feature extraction layers, and the dense neural network on top, these 3 dense layers, those are the simple classifiers. And most of the adversarial problems come from this dense network. Even though it also you have, it's not, also the convolutional layers, you can generate, you can find directions where very small changes explode over the, grow very largely across the layers. But we are not specifically looking for those, right? So we are just asking, when you start with a random example, with a random image, how close you get to the original image if you constrain that. And so you could say, we will only look at typical outcomes. But yeah, I will mention that the serial examples at the end of my talk again, so then we can discuss more. Unfortunately, I still don't fully understand why. Let's talk about it later. So now I want to give you one big picture before I go on. So basically, we think of the visual pathway, and similarly of the neural network, to turn image pixels into some semantic image understanding. And so this is, and we think there's some correspondence, and now we want to use those artificial neural networks as a tool to explore also the activations in the brain. And so it would be cool if, in order to test this correspondence, if we test what the change induced in this artificial neural network what kind of change, whether that would generate the corresponding change, or where this change is encoded in the brain, right? And so for that, it would be nice to be able to generate images that reflect this change. So basically finding an image that acknowledges the change that you have imposed on your representation, and then test in another vision system what this change does to the other vision system. For instance, if you change the appearance of the image, whether, yeah, where that shows up in this other system. And yeah, so in order for probing the brain, textures are particularly useful because they are stationary across space, so you don't have to worry too much about this specific position. And there's also, what is a texture? So it has been also investigated quite a lot by Schulisch, and his idea about textures is that basically for certain things like the forest, we don't really compute every single detail of the forest, but we only represent certain summary statistics about it. And so every forest that generates the same summary statistics responses should be perceived as the same texture. So this is the idea of textures, that it is a lossy representation that makes a spatially, that makes an assumption about spatial homogeneity in the statistics, and that basically you average the statistics across space, and these summary statistics are the ones that are relevant to our perception. So in order to model the perception of textures, basically the question is, can we find the summary statistics that are useful to characterize textures? And so that means, what does it mean to characterize textures? Say we specify certain summary statistics and we have a certain outcome. Then if we have a new texture, it should generate the same outcome. So we have a new texture of the same type. And so this texture is actually a different one from this one. Okay. Sorry, it wasn't. Oh, this is bad. Okay, so now the idea is to use this, if you have certain summary statistics, also to do a pre-image search whether we can find the set of all possible text for. According to these summary statistics, the set of all possible textures that lead to the same outcome. And we can then check whether they are also perceived by us as being similar. And so the better the summary statistics captures what we perceive as similar, the better our texture model is. Or the closer these summary statistics are to the information that is represented in the brain. Okay, so that's the general idea about it, and in end of the 1990s, Betghe and Bergen, Pottier and Simoncelli have been building texture models based on early vision models with the stable pyramid filters. And so the only new thing here that we are doing is that we replace the steerable pyramid by the convolutional network. And using those features to do texture synthesis. Okay, specifically we use the VGG90 network, which was second place in Imagenet 2013, and it only consists of two operations. So one is 3 by 3 by k rectified convolution. So the receptor fields are very small in space and always across the entire feature map. And then you have these 2 by 2 max pooling step in between. So there's no other variation, so that's very simple architecture.
So isn't the set of conv5 that you say at the top, it's the 3 by 3 framework that you use?
So the convolution is always so the transformation from one layer to the next is always a 3 by 3 by k. So this is how it looks for this image. So these are 3 filters actually from the VGGNet. And so there you have 3 by, in the first stage you have 3 by 3 by 3 because the input image has RGB, 3 color channels. And then you have the rectification, and this is how the 64 feature maps look for this image. And then what the next layer does is exactly the same. So you have now 3 by 3 by 64 filters. They are harder to visualize because you cannot color code them also. Then you have rectification again, and this is how the next feature maps look like. And so on. This is max pooling. So max pooling means you take a 2 by 2 area and take the maximum over that area. And in this way, the image size is reduced by a factor of 2 in both directions. Yeah, in this way we obtain a multi-scale filter bank, and so at each layer we consider those outputs as features, and what we use as texture features is, so what we need is something that gets rid of the spatial information. So the simplest thing that you could do is to just average over states. The second simplest thing that you can do is that you take a correlation matrix. So something like the autocorrelation function, if it was the function space here. So if you empirically estimate, it's just the scalar product between all feature maps that you can build. So if you have 64 feature maps, you afterwards have a 64 by 64 matrix containing the scalar products between all feature maps in your layer. And since the scalar product is a sum over spatial positions, so that you don't know which pixel multiplications contributed to the outcome of the scalar product. So in this way, we obtain, so we do this for one layer within each pooling stage. In this way, we obtain 5 gram matrices. And now we do the same reconstruction approach or pre-image search approach as for the image synthesis. Yeah. So I will skip over this. You can go through the slides in details. You can use the machinery that is provided by the neural network toolboxes. So it's just propagating gradients through the network. You evaluate, so here's your, basically you can think of it in 2 neural networks. One which generates your target gram matrices, and here you have a neural network with exactly the same filters. And you start from a white noise image, You evaluate the square distance between the GAN matrices, and then you propagate the gradient back in order to update your original image to make the output of these GAN matrices more similar to the target GAN matrices. And then you feed in this again into the network, determine the distance, and compute the gradients, propagate them back to an update, and if you do that several times, you can synthesize new textures. So these were the original target images here, and these are new images. It's the easiest to see for an image, original image which actually wasn't a texture. For this one, it's actually hard. I mean, you have to look closely to see that it's a new one. So the perceptual quality is very, very good of these OpenCV features for texture synthesis. So, yeah, to make a test, which image is the original, which side is the original for this image here? Right one? Who says right? Who says left? Okay, I think collectively you still see it. So it was actually the right one. And yeah, so for simplicity, it's always the right one. Yeah.
So this, like with the gram matrices, you're trying to match the two last gram matrices, or you're doing
All the gram matrices, all the 5 gram matrices. Mm-hmm. I mean, you can also do individual ones, but it doesn't hurt to add more constraints and so on. Yeah. Okay, so here are some more examples, just to give you an impression of how well it works. So here, the biggest failure of the network is like really long-range linear structures are not preserved. Okay, you can also, so this addresses your question. If you only take the first layer, the textures, the geometries of the first layer, it will look like this. If you take the first and the second, it will look like this. So we cumulatively added more and more layers here. And this is like using 4 or 5 layers. So an interesting result is you can also use this top gram matrix to try to do the Imagenet classification task. So the Imagenet classification task doesn't care about spatial position. So we would kind of expect that the gram matrix should be a good feature space for the Imagenet task. Right? If you want to have a completely shift invariant object recognition problem, then basically images should be treated as textures to some extent. And that's what we also investigated. So we just trained a purely linear classifier with the softmax on, so just one layer basically on the gram matrix. And if you take a pool 5 gram matrix, then you achieve the original performance. And if you take the pool 4, then you get less performance and so on. So you can see that if you use these texture features in the different layers as a feature space for the object recognition task, where you only do linear classification afterwards, then the performance increases, and it can explain basically what the dense neural network does. But it's in some sense somewhat cleaner. And you can also do another test. You can feed in texturized images and ask whether they are classified similarly. And they actually are. So the blue points here are the original, the classification of the original image with the VGG network, and the green ones is what it does with the texturized images, and so there's a very strong correlation between the two. also for this image. So basically, this is, it doesn't bother the network that this dog is more a dog texture than a dog. But, so if objects are on the scale of the entire image, you can actually sometimes get considerable differences between the two. So this texture analogy holds particularly for objects that are on a size that are, say, at least smaller than half the size of the image, something like that. So you get the biggest differences for big objects. Okay, the summary so far is that this is the state of the art in texture modeling, in parametric texture modeling at the moment, so otherwise you use one-parametric texture synthesis. The texture features disentangle object identity along the layers, and textures from non-texture images map out the state invariance of the network's classification response. So I want to make sure that we don't mess up in time again. Okay. Now we can do this texture synthesis, of course, also with things that we like to look at. So we can use an artistic painting and texturize it. And these textures preserve a lot about the appearance of the image, right? So the color composition, so it's a little bit like the cubists thought about images, so that they are a composition of textures, basically. But what is lost here is the spatial arrangement of the objects. So by construction, textures do only encode relative position, they get rid of absolute position. And this is somewhat complementary to the content representation in the highest layer of this network, which has forgotten already a little bit about the fine details. And if you want to do robust object recognition, you want to be invariant against diffeomorphic perturbations and so on. So we expect these high up layers to be a good representation of the content that is flexible against appearance changes, the most flexible against appearance changes. Now we can ask, okay, can we synthesize images that try to satisfy two different types of constraints, one for such a content representation and one from the texture representation. And we can use different target images to specify what kind of content and texture information we want to combine. Like here, so we could use an artistic image painting to define our texture information, and we can use an arbitrary photo in order to define our content. And that's what we are going to do. So basically, consider here the texture as a way to capture the style of a painting, and the content, the fifth layer, or it's not the fifth layer, it's the one layer, is the content representation. And now, if we satisfy both constraints simultaneously, we get actually this picture as a painting of the work in a similar style as the original painting here. And that's pretty cool, so it's fun to look at these images, and you can come, or you can invite all the classic painters to draw your home tone. So this, I didn't know before, but Van Gogh apparently made a picture from Tübingen, and Picasso did as well. Also Munch, or Turner in windy times. And convincing. Okay. You can also use this to do slide transfer between two pictures, so we can make this image look more like this. But in general, it's easier with paintings because we're very sensitive to like photorealistic, well, perturbations and photorealistic slide transfer. Okay, another route that we are currently exploring is can we disentangle more types of perceptual, more specific types of perceptual information. And one very simple aspect, of course, that one could further disentangle is color. So is it possible that we only transfer the spatial aspects of the texture while keeping the color of our original images? So there's an example I showed you here, 4 different images, and we are using these 6 different styles. So these are images to describe the style, but we don't want to use their colors. So we want to keep the colors of the photos. And so this is Tübingen in the different styles. In the other picture. And so you can clearly see that it's always the same spatial structure, but the rest is still preserved from the original image. Okay, so you can also play around with this at our webpage. If you have enough time to wait, so it can take quite some time to do these computations, you can generate 512 by 512 images for free. And here are some examples what people did. So and we also did a visual Turing test, but maybe I skipped that one. So you also use this website as a crowdsourcing tool to get data about how people judge our style transfer experiments. And that brings me almost to the end, so I will wrap up about the content, then I will tell a little bit about future challenges, open problems. So first I told you about Imagenet and the idea of transfer learning, and I think that's a very, very important idea in deep neural network, in the deep neural network business. In some sense, never start to learn a neural network from scratch, but first try to use as much knowledge that has been acquired already with other data sets before you start. Unless you start with a problem that no one, that's where you expect that nothing generalizes in the past. Then I made this detour about model comparison and for saliency models, how you can use information theory to do model comparison. This is actually something that, so for all model comparisons that I did, I always used information theory, so it's a very general framework. So with the time you get very strong intuitions about about the scale of what one bit means, that one a model is one bit better than another model, and so on. So I find that quite useful. Here this was our demonstration of transfer learning, and then I told you about texture synthesis and image manipulation. Okay, so we are asked to also mention some open problems and important open problems, and one important challenge, I think, is to take the Brazil examples that have been mentioned earlier. So just to explain again what it means, so the classic demonstration that was in this paper, not with this image actually, but I used this one here for illustration. So say an image was correctly classified as dog, and then you can use the gradient search to a minimal perturbation to the input image in order to change the classification of the network. And that's the result. So basically there's no perceptual change between these two images, yet now it's classified as an ostrich. And I think that you can change any object to an ostrich if you want. So in that would be really, so that's actually, so if you use image synthesis as a tool to understand your network, then this is a really annoying thing to have. So we, for instance, for the, maybe one more thing to add. So it's not only that by this gradient search, so where you basically search for one very, very specific direction, you get properties that are not so good, yeah, but also you can generate stimuli that are basically that strongly mismatch how humans would classify the stimuli. So it's, and then you can it's easy to find these discrepancies between humans and these deep neural networks. But for me, like this other aspect of being able to synthesize or to induce changes and get meaningful changes in the input is one of the biggest motivations to get rid of this adversarial problem. For instance, for the saliency maps, so we now have a saliency model which has very high performance in predicting where people look, and it would be cool to manipulate images in order to simplify, maybe get simpler equivalent images that have the same saliency map, and then you can causally test, you can do psychophysics again, whether the model is correct, right, and so on. So for instance, this would generate the same saliency map as the original image. This too, yeah, so which is, here you could say, okay, maybe that's still correct, here are more edges, which could generate this blob here, but then we added in a one prior, and then the most salient part I would predict is here. So far, we didn't even bother to do psychophysics because we knew that this network has so many problems with adversarial examples that we cannot use it to induce these changes that we could test in the psychophysics experiment. Another important challenge is understanding can we learn DNNs with semantically meaningful intermediate layers? So I think one intuition about deep neural networks is that basically our work is hierarchical. Bigger objects are built out of smaller objects. And it would be super cool if that is actually captured by a hierarchical neural network. At the moment, it's kind of fuzzy, right? So ideally, you want to have object recognition with each layer of different scales, and the next layer does the composition of an object from the previous smaller objects. And yeah, the third challenge, which I similarly goes in a similar direction, can we build high-performing DNNs without learning? Because that means that we kind of understand what's important. And I consider the learning at the moment as a way to generate a good hypothesis, and ideally at some point we understand what are the crucial ingredients of representations in order to do efficient visual inferences, such that we can basically handcraft them. And finally, of course, we want to understand intelligent systems, and I think for me, one important aspect about intelligent systems is that they have a comprehensive model of the world. And so far, we have been, we're looking here rather at something what would rather classify as pattern recognition problem. But what would be a holistic perceptual representation of the world that deals with all the sensory input that we get, and that basically defines our perceptual state at every moment in time. We're just finding a sensible representation, even if it's like wrong in many aspects, but roughly captures how we organize, things, how we organize the information coming in all the time together with memory. For instance, whether we have some gist representation that we envision, and then when we focus on something, our attention works together with some rough representation of the scene here, and then the scene here has a somewhat larger representation of where I think I am in the world right now. In Kalitz, it's a great place, no? And so that's, exploring that is good, and so I think it's the way from narrow area to general area. And I think that it also seems quite promising just to add more and more tasks, try to integrate more and more tasks, go to multitask setting. And so I've never expected that Imagenet would make such a big change. And I think by this engineering approach, we can actually step by step make more and more progress. Thanks for your attention. This was actually the original image, and enjoy the machine.
One quick question before we let Neil lecture. So that's one quick question. Yeah.
I need to understand how the texture and the content are combined.
So in either case, you minimize the squared distance between certain outputs. And in one case, you specify the output to use as output top layer of the top convolutional layer, that is for